Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Episode 3, What's the Big Idea? In our last podcast, we looked at the three broad criteria that distinguish science as a unique form of inquiry: that the system studied must be physical, that the phenomena must be observable, and that the ideas must be testable. What we aim to do in this podcast is to continue that discussion of what makes the process of doing scientific inquiry different than processes found in fields such as history or art. You've probably heard this referred to as something like the scientific method. Now, while this term is most certainly a misnomer, as there isn't really a single method to doing science, there are common ways in which scientists think of ideas and scrutinize them. I think that the best way to approach this is let's have us think of a system or phenomena that has attracted our attention. It could be something which we can observe the behavior of, which of course makes that thing physical. Perhaps it's a falling ball. Maybe it's the way certain substances react together to form a similar class of related substances. Maybe it's the types of birds that inhabit an island. As we observe the system, it's pretty likely that we're going to notice some regularity in the system's behavior. We may also recognize that the system behaves like some other system we've observed before, one where we feel like we have a pretty good understanding of what's going on and how to think about that thing, though that's not always going to be the case. In making and recording our observations, we're most likely going to be led to try to explain the system or phenomena in some fashion. And this leads us to the first type of scientific idea, the scientific hypothesis. So, what is a scientific hypothesis? A scientific hypothesis is a description or explanation of a system or phenomenon that allows someone to make a falsifiable prediction about the behavior of the system in a new or previously unobserved situation. So, where does a scientific hypothesis come from, and how do scientists create them? These types of questions are the kind I get asked most often by my students. Since many of them think that science is little more than a collection of facts, they wonder how a person can come up with a new idea and have that idea actually mean something. They think, since it's not proven, why do we waste our time on it? More importantly, they're concerned about how a scientist knows that the idea is right. Martin Fisher has a wonderful quote on this misconception. He said, "Facts are not science, as the dictionary is not literature." In other words, just as literature is more than a collection of words on a page, so too does science go beyond a mere collection of things we know about the universe. While literature certainly starts with words, those words are organized according to various rules of grammar to form rhetoric. Literature is the creative use of language in order to express ideas so that a person can understand what is taking place in the mind of the other. In the same way, science starts with pieces of information that we know about the universe, but then constructs those pieces of information in such a way and according to certain rules so that we better understand the universe. Science, like every other form of inquiry, requires an engagement of an individual's creative talent to imagine things and then use what has been imagined to further probe and understand the subject. Remember what we said in a previous podcast. The purpose of science is to understand the relationships of things in the physical universe. The way scientists come up with hypotheses is that they take what they have observed and they use their creativity to come up with a description of what they see and sometimes an explanation of how or why it happens. They can base that description on anything as long as the description allows them to be able to say, if this happens, then the system will do that. The basis for this can be something as tentative as a guess to something grounded in having observed what the system has done in a similar but not exactly same situation. Now, usually a hypothesis falls somewhere between these two extremes, but a lot is determined by how much the system or phenomena or something like it has been previously studied. As more information on the system is discovered, the hypothesis goes from being something closer to that tentative guess to being more of an educated guess to being something a lot more than that. A great way to think of this is to imagine you had 20 people in a room and a 500-piece jigsaw puzzle. Now let's say each person is given one piece of the puzzle and asked what they might think the puzzle might be a picture of. Their answers to that question, in other words, their hypotheses, are probably going to be pretty vague at first, and they're not going to agree with each other very well. But now, let's say you repeat that process 5 more times. With each additional piece of the puzzle, a person's going to get a little bit more information about the puzzle, and they're likely going to give you a more specific answer each time of what the puzzle is showing. This is a bit like hypothesis formation. Additionally, as the group each gets more information, their hypotheses are probably going to converge more closely to a common answer. As we go forward, keep this example in kind of the back of your mind, as it's going to help you understand a little bit more about what we mean when we talk about hypothesis formation. A historical example of this in antiquity is when electrostatic discharge was first observed in pieces of amber. In that example, the descriptions of the phenomena and the explanations of it ranged from the amber having a coating to things having souls. Over time, as these sorts of systems were studied in greater detail, the descriptions of what was going on would change and become more specific. Electricity was, over time, thought to be a fluid, then thought to be a movement of charged pieces of matter. Additionally, it was once thought that electric forces and electricity and static discharge and lightning and storms were all completely different physical phenomena. For millennia, actually, the best human hypothesis for lightning was that it was something thrown at people by a cranky, superpowered being who lived on a mountain and didn't like us very much. However, over time, it came to be understood that all of these things were just different expressions physically of the same underlying natural reality. A really important thing to understand is that a scientist who has the hypothesis doesn't actually really know whether it's right or not. And the thing that's even more interesting, I think, is it doesn't really much matter whether it's actually right or not. The most important thing about a hypothesis, and the thing that makes it scientific, is that it can be tested and shown to be wrong. It's the process of making predictions and then testing them that allows us to move from something where the correctness of the idea is unknown to something that is a valid and useful explanation of what is happening in reality. This is something that many of my students have a really hard time getting their heads around. They think that science is something that should be correct from the very beginning. They don't see it as a self-correcting process that works towards getting a more accurate description of a system through a process of imagining an explanation for an observed phenomena and then testing that idea. They struggle with that reality that sometimes just as much can be learned from being wrong about a physical system as can be learned from being right about it. So the next question is, how do we get from a simple hypothesis to the more complex and fundamental ideas often discussed in science? The way we do this, of course, is by gathering information in the ways we talked about in the last podcast. More specifically, we try and devise tests to see if our explanations will work beyond in predicting what the systems will do in those test cases. Doing this is a special type of observation known as an experiment. So, what's the difference between an observation and an experiment? We've been talking about making observations, and now we need to be a little bit more precise about what the terminology means here. In an observation, a scientist can control the way in which the observation is made. She can pick the observation with which she wishes to make the observation, the procedure for making the observation, and the data she wants to keep track of. What she can't always control is the system she is observing, either in some important part or maybe at all. As an example, let's say she wanted to make observations of the sun. She could choose to use a heliograph as her instrument and measure the light using a diffraction grating to produce the spectrum and record the data with a CCD camera that is accurately able to record light intensities at a number of different wavelengths, let's say a 1 nanometer accuracy. However, she cannot control anything about the sun and what it is doing. Observations are generally limited in this way. Now, when we are able to control the system being studied, we call that an experiment. Let's say I want to study falling objects. I can pick the object I want to drop, the height from which I will drop it, and the location where the experiment will take place. I can decide I want to measure the amount of time it takes from the moment the ball is released until the instant it hits the ground, and then I want to measure that with an automatically triggered timepiece that measures to the thousandth of a second. In this case, I control both the system being studied and the means by which the observations will be made, and thus I am doing an experiment. As you can imagine, experiments are much more useful in testing the if X, then Y types of predictions we'd like to be able to make using a hypothesis. Unfortunately, in nature, there are a whole lot of systems I might want to study that I just can't control, whether those be distant stars or the behavior of volcanic mountains. This also extends to things I want to study that might have taken place in the past, such as fossil remains in sedimentary rocks or meteor impacts on the moon. The most classic type of experimental design is for the experimenter to account for all of the things that might vary and then to allow only one of those to change in a controlled fashion. As that one thing, which is usually called the independent variable, is allowed to change, the scientist measures or observes the system for any changes in a variable that is thought to depend on the independent variable. If there seem to be changes, the experimenter records this and then compares it to the changes in the independent variable and looks to see if there's a relationship between the two. If there is, then this relationship gets included into the hypothesis that describes the system. Now, what should be understood is that the relationship has only been shown to actually work in the case the experiment is really tested. While the observed behavior of the system and the relationship between the independent and dependent variable is now an established fact, this knowledge is not considered to be absolutely true in other cases where the system or environment may have been changed in some way. What can be done, however, is that the hypothesis can be used to make predictions about what the system will do in similar but untested conditions. In fact, if the hypothesis can't do this in a way where the test could produce a result that contradicts the hypothesis prediction, then the hypothesis is not considered scientific. Additionally, if the prediction is such that it is untestable using the means available for a significant period of time, the usefulness of the hypothesis as a tool for inquiry is often called into question. Such is the case with string theory and many of the predictions it makes. At present, the technologies available do not allow for the testing of string theory, and thus it is rightly held at arm's length by many scientists who may find it a very interesting hypothesis, but who consider it somewhat speculative for the time being. At this point, a more concrete and down-to-earth example is probably going to be helpful. Consider the idea of falling objects. Let's say that one day I'm playing ball with one of my golden retrievers, and I notice that when I drop the ball, it falls, of course. But let's say that in the course of the game, I get to wondering about the nature of the ball's fall. Does the ball fall with a roughly constant speed, or does the speed change? Does it matter if the ball is a regular tennis ball, or one of those bigger and more dense dog kongs that you can buy? So being a good scientist, I decide to conduct an experiment with a well-defined protocol to make a few measurements about how the ball falls. I decide that the controlled variable will be the type of ball, and the independent variable will be the height from which I drop the ball. What I will do is measure the time of fall as the dependent variable, and if the ball takes twice as long to fall twice the distance, then I can say that the ball moves with a constant speed during the fall. Now let's say I do the experiment, And I find that the ball takes more time to fall twice the distance, but less than twice as long. In other words, the ball covers the second half of the longer fall in less time than it took to cover the first half. This means that I know that the ball was moving faster the further it fell. Another way to say this is that the ball underwent accelerated motion and sped up. The first scientist to do this sort of experiment was someone you may have heard of, Galileo Galilei. We'll have a whole lot to say about him down the road, but in this instance, he determined that objects dropped near the surface of the Earth fell with a certain acceleration. In the units that we tend to use in science today, the number for that would be 9.8 meters per second per second. What that means is that each second the ball is falling, it is traveling about 10 meters per second, or if we put it in imperial English units, 32 feet per second, faster than it was the second before. Now, if I've conducted these experiments in the 4-story lobby of the building I teach in, then what I can say is that tennis balls fall with an acceleration of 9.8 meters per second in the instructional complex at Gordon State College. What I don't quote-unquote know is whether the ball will do that anywhere else. I also don't know if it's true for a dog Kong or a basketball or, say, a feather. This is where my hypothesis can help. If my hypothesis is that all tennis balls will fall with an acceleration of 9.8 meters per second squared anywhere on the Earth, then I can conduct the experiment in another location, say a hotel with an open atrium in Atlanta or at a high-rise building under construction in New York City or Beijing, China. The prediction of the hypothesis can be tested, and since the test has the possibility of showing that the hypothesis could be wrong, we can say that the hypothesis makes a falsifiable prediction, which, as I mentioned before, is required for a hypothesis to be scientific. Each time I test the hypothesis, my explanation gains credibility, even more so if other scientists confirm my data and conclusions. Because remember, what I'm supposed to be doing is publishing my data or communicating with other scientists in such a way that they can replicate my experiment. At some point, perhaps I can test other kinds of objects such as iron cannonballs and grapefruit, like Galileo or one of his students is supposed to have done from a certain beautiful but not quite vertical architectural structure. In time, I might gather all of these results that have confirmed my explanation into something that I think explains what a set of similar systems does in a broad set of circumstances. When I do this, the explanation is often called a scientific law. Galileo did this with the following objects he and his students had tested and called the explanation the law of falling bodies, which went something like all compact and dense objects that move vertically, i.e. up or down, will move in such a way that they have an acceleration of 9.8 meters per second towards the ground, meaning that they will slow down at that rate if they're moving upward, and they will speed up if they are moving down. So what makes a scientific law different than a scientific hypothesis? What's important to notice here is that there is no attempt to explain why the system behaves in this fashion. One way to define a scientific law is to say that it is an explanation of a physical system that predicts what the system will do in a given set of broad circumstances, but that does not explain why the system does that. Historical examples of scientific laws are things like Kepler's 3 laws of planetary motion, Newton's universal law of gravitation, and the ideal gas law. By the way, this last law is actually a combination of 3 earlier physical laws describing the behavior of many gases that were known as Boyle's law, Charles' law, and the Gay-Lussac law, showing that more narrowly defined relationships and descriptions of physical systems can be integrated into broader and more general descriptions. Now, what happens if an experiment or observation gives a result that indicates that the hypothesis has made an incorrect prediction? That's a great question, actually. So, we've talked about what happens when a hypothesis describes a system and is able to make correct predictions about the behavior. But what happens when the hypothesis fails, when it doesn't make a correct prediction? To examine this, we need to do a thought experiment for our example. Now, by the way, doing a thought experiment means that what we need to do is we need to imagine what could take place or what could happen for the sake of argument in a situation where we really can't actually do the experiment. This is something scientists do very, very frequently. So let's say in our example, we could travel to the moon with our tennis ball, something that we can't actually do, but we can think about, hence the term thought experiment. Our law of falling bodies would predict that the ball will fall with an acceleration of 9.8 meters per second squared. Now, if we were able to do this experiment, what we would find is that while the ball does fall and does accelerate while doing so, the rate of acceleration is only 1.6 meters per second. Now, for us, this is a thought experiment, but the Apollo 14 astronauts actually did go to the moon and did do an experiment like this, which if you go out to YouTube and you search for this, you can find the video that shows their experiment of dropping a geologist's hammer in this case. What this means for us is that the law of falling bodies has failed to correctly predict the outcome of the experiment and has thus been falsified. So what do we do now? Well, generally, the first course of action is to modify the hypothesis. The reason for this is that we know it works for every case we've tested on Earth, and it was only partially wrong on the moon. So there's a good chance that we just need to tweak or modify something in the explanation of how the system works, and we'll be back in business. This kind of thing takes place frequently in science. As new data is gathered and new situations are investigated, scientific ideas are often modified when necessary to take new data into account. Now, in the case of the law of falling bodies, Isaac Newton actually figured out how to modify the hypothesis long before we ever went to the moon by using his 3 laws of motion and his universal law of gravitation. Sometimes, however, the hypothesis is so wrong and flawed that it must be completely rejected, and scientists have to come up with a completely new explanation of a system's properties and behavior. An historical example of this occurred shortly after J.J. Thomson discovered the electron. Now, we'll spend a couple of upcoming episodes talking about this process in detail, but in trying to explain the structure of the atom and how it might incorporate the electron, Ernest Rutherford and his group of experimenters at Cambridge's Cavendish Laboratory arrived at experimental results that showed that no existing hypothesis of the nature and structure of the atom was actually correct. The team had to come up with a new description of the atom that agreed with their data. This description, sometimes called the Planetary Model, was the first description of the atom to have the now familiar compact nucleus and orbiting electrons. In either case, it should be noted that even though the original hypothesis was wrong, the testing that it led to uncovered new information that helped scientists move towards a more correct description of the system. This is why I said earlier that it wasn't as important that a hypothesis be right as it was that the hypothesis be able to make testable predictions. Additionally, it is important to note that such modifications can be made to any scientific idea at any level if new data is gathered that the idea can't account for or didn't accurately predict. So the next question that I like to talk about is, what's a scientific theory then, and how is it different from a hypothesis or a law? This question leads us to our final type of scientific idea. Usually, once a hypothesis or group of hypotheses becomes a scientific law or set of related law, the laws, models, and organizing principles that comprise the description begin to guide scientists to discovering the causes of the system's behavior by giving clues to the underlying activities that are taking place in nature. This leads to new experiments and observations that will add to the picture until there is an understanding of not just what happens in a given set of circumstances, but an explanation of why those things happen. In this case, we try to call the description a scientific theory. It is very useful here to emphasize the difference between a scientific law and a scientific theory. Scientific laws describe what is happening, while scientific theories explain why things are happening and thus are always more capable of correctly predicting what will happen in a new circumstance. Unfortunately, this nomenclature is actually counter to how we usually use these two words. In our everyday language, a theory is usually just an informed but untested guess about what we think might be going on in a certain set of circumstances, while a quote-unquote law is something that has a sort of binding force that can't be broken. This type of idea is taken from our understanding of jurisprudence or the legal system. Thus, we tend to think of laws as being much more ironclad and correct than theories, and that they should be unbreakable. As you can plainly see from our previous discussion, however, this is not how scientists use those words, and such an idea is based in a deep misconception about how science is done and the nature of scientific ideas. In science, every description of a system, no matter how well it has been tested and no matter how long it has been held, is open to revision based on new data if that data contradicts a prediction that the description has made. Laws are laws because they have survived more tests than hypotheses, and they explain what a broader class of systems will do in a wider variety of circumstances. Theories are held in higher regard than laws because they've survived even more testing, and they explain why systems do things. This ability to explain why indicates a deeper level of understanding than just being able to predict what might happen. Thus, things like the theory of quantum mechanics, the theory of plate tectonics, the theory of general relativity, and the theory of evolution aren't just half-baked ideas that haven't really been tried out, but rigorously tested descriptions of systems that show a deep understanding of the fundamental processes and relationships that govern the natural world. In my experience, some of the misconception between the scientific community and the general populace about the nature and validity of scientific ideas and explanations come down to the differing use of the very same words. The word theory means something very different to a scientist or when used in a scientific context than it does in an everyday one. A great example of this can be found in many of the popular crime dramas found on network TV. Over the last decade or so, a version of this genre that focuses, at least in part, on the analytical work of a forensic scientist has become pretty popular, beginning with the show CSI. One of my pet peeves about most of these shows is that they commonly use the word theory when what they really mean is hypothesis. An example of this might be when one of the supporting cast tells the main forensic scientist that they have a theory about what might have happened in a particular crime scene to produce the evidence that has been found and cataloged. The two characters then proceed to test the idea. As scientists, the word they should have used was hypothesis. This bugs me enough that I used to correct the actors as I watched the show. Well, I did until my wife told me that if I wanted to watch the shows with her, I needed to stop. One of the little burdens of being a scientist, I suppose. The last point I'd like to make about this is that not all naming follows this general guideline. Historically, people named ideas using what seemed best to them without always having a clear picture of what was happening, or, more often, they did so before a strong set of guidelines developed within the scientific community. As such, nowadays, many philosophers of science have more or less discarded these distinctions when discussing scientific ideas, recognizing that regardless of the explanatory nature or power of the idea, all scientific descriptions must meet the basic criteria of being physical, observable, and testable. Philosophers are increasingly calling all descriptions scientific theories, as they are much more interested in understanding the fundamental role descriptions with these properties play in the process of inquiry itself. In the next episode of the podcast, we'll take a look at a couple of the tools that scientists use that can help them shape the types and directions of their research in order to move through scientific ideas in the stages we've discussed here. So until then, full sails on your journey.